Hi, this is Professor Fernandez, and in this video we are going to work out an example of the radius of convergence of power series. This example comes from the notes for lesson 11. You can find those on this site, and you'll find these other resources there as well. So power series. So let's talk about power series first, and then we'll talk about the radius of convergence of power series. So I'm going to do a little review of that. It'll probably take me a few minutes, so if you want to skip ahead and just would like to see the calculation of the radius of convergence for these two particular examples, you're free to do so. First thing I'll do is I'll zoom in a little bit and remind you a little bit about power series. So thus far in the course, we had been studying infinite series. So those look like this. Sometimes n started at 1, sometimes it started at 0. Didn't really matter. An example is something like this infinite series, right? So this is 2 to the first, plus 2 squared, plus 2 cubed, and so on. We were most concerned with convergence or divergence of infinite series, right? This one diverges. All sorts of ways to show that. You can use the divergence test, for example. The limit as n goes to infinity of the an terms is not 0. So the series diverges. But what if, we now switch gears a bit and we consider, quote, infinite series that have variables in them. And remember, we got to this by looking at the geometric series, AR to the n, which converges to a over 1 minus r, so long as absolute value of r is less than 1. And then we kind of just set a equal to 1. There we go. And then we literally switched the letters. So replaced r by x. And we got this really, really interesting result that says that the function 1 over 1 minus x is equal to the infinite series, maybe, it's not an infinite series of numbers, sum of x to the n, so long as absolute value of x is less than 1. So where we are in the course right now, we're still trying to make sense of this baffling result, because the thing on the left-hand side is not an infinite series in this sense, right? Sum of numbers, infinite sum of numbers. It's an infinite sum of, powers of x. And yet we know that it equals a function, right, on a certain interval. So there's a lot to unravel there, but that's kind of where we are in the course, and we're trying to make sense of all of this. So we figured that we would study a more generalized version of these types of, quote, infinite series. Here you have a power of x multiplied by 1. So what if we allow the coefficient to vary with n? That's the a sub n. And what if we, instead of just a power of x, we allow a power of x minus c? So that's how we got to power series. And that's what is, I'm just trying to erase this, see if it'll let me. Power series, therefore, is where we are now in the course. And the thing I just erased, right, the absolute value of r less than 1, absolute value of x less than 1, is some information about convergence information, right? For infinite series, the convergence divergence information was pretty straightforward. It either converges or it doesn't, right? It diverges. For power series, it's a little less straightforward. And actually, I'm going to go back to this example that we're going to do here, and I'm just going to illustrate that real quick. Long story short, the convergence or divergence of a power series depends on the x value that you substitute into it. So let's take a look, for example, here at if I put in x equals 3 into this power series, it's going to go up there. So it'll be 3 minus 2 to the n. That leaves me with the infinite series of numbers, 1 to the n times 3. 1 to the n is just 1. So this is the infinite series, 3 plus 3 plus 3. This diverges. Okay, but we can't take that and then say this power series diverges. Because look what happens if I plug in, let's say, x equals 2.5. Okay. If I put 2.5 up here for x, then the infinite series is 2.5 minus 2 to the n, summing from 0 to infinity. Okay, so that's 3 times 0.5 to the n. Hey, that's a geometric series, where this is a and r is 0.5. And because absolute value of r here is less than 1, this geometric series converges. Okay, I think we talked about geometric series in lesson 6, so I'll send you over there to the notes and or videos for that. But the point is that this power series therefore converges for x equals 2.5. It diverges for x equals 3. And so that brings up the question, what are the set of x values for which this power series converges? For example, would 2.6 work? How about 2.7? How about 2.689? Right? So it'd be nice if there was a systematic way to figure out that set of values for which, x values, for which the power series converges. And there does turn out to be such a systematic way. Long story short, it's going to involve the ratio test, and we'll do that in about 2 minutes, right? But between now and then, I have to tell you about a nice little theorem that gives us the only 3 possibilities for what power series convergence could look like. So that's this theorem. This is in lesson 11. So what does it say? For a power series centered at C. By the way, if you look at a power series, it comes in this standard form. The center of the power series is the C value. So for example, this power series is centered at x equals 2, right? Because the C value is 2. Okay, so theorem says for a power series centered at C, only one of the following is true. So either this, either this, either this, but not 2 or more of those. First of all, the series converges only at C. Okay, I'll say that this is an extreme example of what could happen. A power series always converges at C. Why is that? Because if I substitute in x equals C, right, then because C minus C is 0, 0 to the n is 0, an times 0 is 0. This is just literally the series 0 plus 0 plus 0 converges to 0. So a power series always converges at x equals C, the center. However, what may happen, and we're kind of being told here, is that the series could converge only at C. All right. What's something else that could happen, though, right? So it might also happen that there exists a real number, a positive real number, such that the series converges absolutely for this interval and diverges for that interval. Okay, so what does that mean? Now I'm going to switch over to a number line way of illustrating this theorem. If I consider a number line where these are all x values, the first possibility says that only x equals C leads to convergence. So it's just a dot there on this number line for x. The second possibility says that in addition to x equals C, there is an interval, an open interval, that goes all the way to C plus R and all the way back to C minus R. And for all the x values in this interval, the series converges absolutely. That's very nice convergence. And I'll send you to lesson 8 and the videos there to review what absolute convergence means. Long story short, it means that the series of absolute value terms, the series you get by making all the, taking the absolute value of all the terms, converges. That's what converges absolutely means. Okay, so if you're in this interval, this second case says the series diverges in this interval, converges in this interval, and diverges for all x values outside. All right, and then number 3, it says converges absolutely for all x. So continuing in this number line visualization of this theorem, it's like saying, again, always converges at C. It's like saying the entire real line, right, converges for every single x value you could plug into the power series. So this is a visualization of the 3 cases of this theorem. And notice that each of these can be recast in terms of this number r. So over here, r equals 0, right? You converge at x equals C, but you can't move beyond it, right? Over here, r is positive. You converge at x equals C, and you have a little more wiggle room, right? X values just to the right of C, just to the left of C inside this interval lead to convergence of the power series. Over here, r is infinite. Like you can go as far away from x equals C as you want. Plug in an x value there, power series will converge. So because of this centrality of r, right, we give r a special name. It's called the radius of convergence. And then one thing we have not talked about is, for example, in this case, do you converge at this point so that the interval is half closed? Do you converge over here, so half closed this way? Or do you converge at both endpoints, so it's actually a closed interval? Good question. That's called the issue of convergence at the endpoints. Once you decide that, once you figure that out, and you do that by plugging in these specific endpoint values into the power series, generating an infinite series and converging or convergence tests, applying a convergence test to that. Once you figure that out, you get one of these 4 types of intervals, right? Open, half closed this way, half closed that way, or closed. That interval then tells you exactly, or right, the entire real line, which fits into here. That interval is the final interval over which the power series converges, on which the power series converges. And that is called the interval of convergence. Okay, so we've now reviewed literally everything that could happen in terms of convergence or divergence for a power series, and all the terminology. So now let's go ahead and actually apply that to all these examples. Okay, part A here, right? So I'm going to find now the radius of convergence. This example is not about the interval of convergence. We're just finding the radius of convergence. So we're looking for R. And I mentioned earlier, kind of forward-looking, that we were going to use the ratio test to do this. That's the main test that we use to find this radius of convergence. So I'll send you back to videos 10.1, 10.2, where we talked about the ratio test and we did a few examples of using it, in case you want a refresher. Long story short, here in the ratio test, I always recommend that you take the entire expression of the sum and make that your a sub n for the purposes of the ratio test. And then we need a sub n plus 1, the next term. You just plug in n plus 1 into that an expression. Then we need the ratio and the absolute value of that. So here we are doing this, n plus 1 over 3 x minus 2 to the n. In many of the examples in these videos, when we use the ratio test, we ended up not needing the absolute values because all the terms in the series were positive. When you're doing convergence of power series using the ratio test, definitely leave in the absolute values. It's really important. You'll see why in a minute. So if I keep going here, the 3's cancel. This x minus 2 to the n cancels with one of the x minus 2 to the n's, right? Here, this is x minus 2 to the n times x minus 2 to the first. Cancels with that one. So I'm left with absolute value of x minus 2. Okay, and then the ratio test says, take the limit as n goes to infinity of the absolute value of the ratio of successive terms, which in this case is x minus 2 absolute value. And notice that this thing does not involve an n. So it comes outside the limit. And we're taking limit as n goes to infinity of 1, which is just 1. Like the function 1 just stays 1 as n goes to infinity. So the answer to the limit is x minus 2 absolute value. Okay, you might be a little confused at this point, right? If you've done the ratio test, if you watch this video, usually we get a number for the ratio test, like, I don't know, 7. And then we compare that number to 1. If it's bigger than 1, something happens. If it's less than 1, something happens. If it's equal to 1, something happens, right? We didn't get a number here, right? So we just got x minus 2 absolute value. So here's what we do. We say, well, in the ratio test, whatever you get from this limit, right? The only way that you get convergence is if whatever you get from this limit is less than 1. That's literally the ratio test theorem, right? So we're going to set this less than or equal or less than 1, really, because that's the ratio test theorem. And then, because of the ratio test, it says that for whatever x value I plug in to the original series, as long as absolute value of x minus 2 is less than 1, I will get convergence. Okay, so I'm going to write that conclusion down and then kind of explore it with you a little bit and tie it back to some of the types of calculations we were doing at the start of the video. So we have found that, I'll write converges. We have found that converges for absolute value of x minus 2 less than 1. Comparing this to number 2 here, right? X minus c, absolute value less than r, right? X minus c, absolute value less than r. Notice we can make a few identifications, right? Certainly we knew that this is a power series centered at 2, so for sure c is 2. But now also we can take a look at this identification here, right? So r equals 1. And that actually answers the question that we were out to answer. We set out to answer in this example. What is the radius of convergence? Radius of convergence is 1. Okay, And now what would I do with this, right, if I wanted to, again, explore this a bit further, tie it into what we did earlier. So now this is kind of going beyond what is asked. Absolute value of x minus 2 less than 1. So let's unravel that. So that's x minus 2 less than 1 and bigger than negative 1. Then I'm going to add 2 to both sides. So that's 3 on the right and 2 minus 1, or 1 on the left. This is now an interval, much like the one that I was showing you earlier in the video to explain the theorem that we were talking about. And therefore, we know for sure that for any x values in this interval, the power series 3 times x minus 2 to the n, as n goes from 0 to infinity, converges. If you rewind the video all the way to the beginning, right, we explored x equals 2.5, that's in here. We also explored x equals 2.6, that's in here, right? So those are examples of x values in here. But also about over here, like 1.5, 1.7, 1.9, even 1.1, right? So those are all x values over which such that if you plug it into this infinite series, you get a power series, you get a convergent infinite series. Okay, and this also tells us that the theorem does, that if I plug in x values outside, right, of this interval, then I get divergence for the power series. The theorem doesn't tell us, again, about the endpoints. So we could plug in x equals 3 and investigate that. We also could plug in x equals 1 and investigate that and see if the series converges or diverges there. We won't do that here because, again, the point of the example was to find the radius of convergence. Okay, so instead we'll look at the second example and then wrap this video up. So let's take a look at that second example. It says sum from 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial. Okay, so the an term here is x to the 2n plus 1 over 2n plus 1 factorial. And then I'm going to put in n plus 1 here. So everywhere I see an n, I'll put in n plus 1. And then down here, I'll put in n plus 1 as well. All right. So I have x to the 2n plus 2 plus 1 over 2n plus 2 plus 1 factorial. That's a mouthful. So because we're going to end up finding the quotient of an plus 1 and an, I'm going to group this one and this one, x to the 2n plus 1, and then there's an extra x squared left over, right? Divided by, and then over here, I'd like to relate this to this. So here's a 2n plus 3, 2n plus 3 factorial. Remember back from the videos from lesson 10 where we had talked about the ratio test using factorials. I think that was video 10.2. The property of factorials, 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. We could keep going, right, and then be a lower factorial, but I stopped there because that one is here. So this is 2n plus 3, 2n plus 2, and then 2n plus 1 factorial. Okay, great. So now next step, form the ratio an plus 1 an, absolute value. So it's that whole thing, x to the 2n plus 1 times x squared, over this 2n plus 2, 2n plus 1 factorial, divided by this thing up here. So multiply by the reciprocal over x to the 2n plus 1. Okay, before proceeding with the calculation, because it's now gotten quite involved, let me pause and go back to some of the intuition we had developed in earlier videos, earlier lessons, right? This is a factorial down here. This, x to the 2n plus 1, this is a power function. So going back to the infinite series intuition we had developed about when they converge, if the terms go to 0 fast enough, we expect the infinite series to converge. That same intuition carries over into power series. 2n plus 1 factorial goes to 0 really fast, certainly faster than a power function. So we expect this infinite series to not just power series to not just converge, but converge for all x. That would be equivalent to getting r equals infinity. Okay. All right. So now back to our scheduled program, right? X to the 2n plus 1, those cancel. 2n plus 1 factorial, that cancels there. And everything is absolute value. So I have absolute value of x squared over 2n plus 3, 2n plus 2. Okay. And then now I take the limit as n goes to infinity of this ratio of successive terms in absolute value. That's the limit as I goes to infinity of this thing. Okay. X squared over 2n plus 3, 2n plus 2. And notice then that the absolute value of x squared comes out. The thing that's left has 2n plus 3, 2n plus 2, and n starts at 0. So that's all positive, don't need the absolute values. And then, because n goes to infinity and the only n's are in the denominator, right? And it's just a quadratic function of n, this limit is 0, right? Times 0 equals 0. Going back to the ratio test, we ask the question, is this less than 1? Yes, it is. And then here's the crucial bit. Not only is it less than 1, so it converges, it's less than 1 no matter what x value you substitute in there, right? X could have been a trillion, and we would have squared it, taken the absolute value, but then multiplied it by 0. That would have still gotten a less than 1 result, convergence by the ratio test. So when you get something like 0 for these calculations, when you're doing power series using the ratio test, that tells you that the radius of convergence is infinite. Because, like we just said, you can substitute in any x value. Listen to that, any x value, right? You imagine the real line, and you can plug in any x value. If you can do that, then the radius of convergence is the entire real line, the integral of convergence. And therefore, the radius of convergence is the entire real line, infinite. Okay, so r equals infinity, like what we have kind of intuited based on our intuition about convergence for infinite series carrying over to power series. And that does it, therefore, for the second example here. There was a lot in this video, took a little longer than usual, but that's because really power series is a new topic, and it builds on infinite series in a way that both complexifies infinite series, but also reveals some really nice properties and extensions of infinite series. So take a look at the video again, and feel free to go back and rewind and move along different parts of it to make sense of the theorem, the definitions, and some of the computational procedures. Thanks for watching.